Good evening, Leeds. Fiat Lux IV, a rather enigmatic title, because some time ago I wrote a trilogy of talks about the nature of light, which I called Fiat Lux, not surprisingly, parts 1, 2 and 3. So this, you could argue, is part 4 of the trilogy. And what I'm talking about tonight is colour in the cosmos. So I'll be giving a short introduction about, before launching into the cosmos itself, looking at how humans perceive colour and how we might quantify the colour that we perceive. Then I'll be looking at the colours of stars and the colours of nebulae. And then I'll finish with some thoughts about spectroscopy, spitting light into its colours, and then thinking beyond colour, the use of false colour. And then I'll summarise at the end. So we could ask the question, the fundamental question, is colour real? Or is it just a pigment of your imagination? Because we could ask ourselves, why do we have colour vision in the first place? Apart from the fact that an image like that, the beautiful rainbow, that would look pretty boring if we didn't have colour vision and the rainbow would just be a band of light. You could argue that we have colour vision because it's useful to be able to tell, for instance, when fruit is ripe so we don't end up eating the wrong stuff. If you look at that, you might ask yourself, if we didn't have colour vision, which, if any of those are ripe and which of them, if any, are unripe? Without colour vision, very difficult to tell. But with colour vision, it is pretty obvious which fruits are ripe and which aren't. I would argue that it wasn't necessarily ripe fruit that demanded that we have colour vision. I think we've got colour vision because otherwise maps of the underground would be impossible to work out. In grey, it's very difficult. As soon as you put the colour back, it's a little clearer what's going on. So maybe that's the evolutionary drive to colour vision. So how do we perceive colour? I think you all realise that the human eye works by taking light, focused by the cornea and to some extent the lens, onto the retina at the back of the eye. And the retina is a collection of photoreceptors, some of which are sensitive to colour, these colour photoreceptors. And these take the light signal, take the light energy, convert it to a chemical signal which ends up getting transmitted down the optic nerve to the brain. And you might say, well, okay, that's sort of what a camera does, isn't it? You know, a camera has a light-sensitive surface. It's not a retina, it's a chip. But if we were to look in detail at that chip, we find a whole load of red, green, blue colour receptors. Strictly speaking, they aren't different coloured receptors. There's only one type of receptor on the chip, but each pixel of the chip has a colour filter in front of it to give us the red, green, blue separation. And if we think of the colour transmission of those red, green, blue filters on the front of a chip, quite often arranged in this so-called Bayer grid, we can see that if we take a camera, this is a camera I owned a few years back, a Nikon, it doesn't really matter which camera we choose. If we think of the transmission of colours, we see that we can transmit in the red, the green and the blue through these three filters. They overlap to make sure that we have a continuous range of colours being picked up. And because each of them only transmits a certain range of the full spectrum, here indicated as 400 to 700 nanometers of wavelength of light. Bear in mind that human vision, being humans, everybody has a slightly different range of colour vision, but I'm going to assume that for most part, anything between 400 nanometers and 700 nanometers are the wavelengths to which we are sensitive. And that's why cameras have been built with a similar colour response. And if cameras have this sort of colour response to red, green and blue, it's tempting to assume that that has been done because that's a good mimic to the way human vision works. If we were to have the same grasp for colour vision in our eyes, would they look the same? And the answer is, well, they look similar but not the same. In some respects, it's quite surprising to find the red and the green are so close together. So you could still label these colour receptors, if you like, red, green and blue. But notice, for instance, that the red receptors in our eyes are actually sensitive to light across the entire spectrum. Okay, not so sensitive at the very red end, but the red curve here clearly goes all the way to 400 nanometers. And similarly, the green receptor is also sensitive to a huge part of the spectrum. It's really only blue that is limited to 100, 125 nanometers or so. And it's because of this that the biologists don't refer to these three receptors as the red, green and blue receptor, because strictly speaking they are not even peaking in the red or the green or the blue part of the spectrum. So they refer to these three receptors as the short wavelength, the long wavelength and the mid wavelength receptors. But for the purposes of clarity, I'm still going to refer to them in this talk as the RGB, the red, green, blue receptors. So it is perhaps a little surprising to find that blue is so different from the red and the green, and we can talk about the evolutionary drive as to why we have ended up with eyes that are sensitive to those particular bands. But before we move on, let me just remind you that as well as colour receptors in our eyes, we also have rods that are not colour sensitive, but generally speaking work at night, particularly important of course to astronomers. The colour receptors tend to only work when the light levels are bright enough, whereas the rods work quite happily in low light levels, but are not sensitive to colour. And you notice that the rod colour spectrum, if you like, the sensitivity range of rods only goes from about 400 to 600 nanometers. There is essentially no sensitivity at all at the red end of the spectrum. And that's precisely why, as astronomers, we use red lights at night, because even a bright red light in principle does not affect the rods, and it doesn't affect your night vision because the rods are simply unaware of any red light. As long as you stick to that end of the spectrum, it's perfectly okay to illuminate with a relatively bright red light so you can see what you're doing. You can read a star atlas, for instance, and yet your night vision is preserved. So we have three sets of colour receptors, so-called trichromatic vision. Some animals have a great deal more. I've shown you what the colour response of human vision looks like, but there are some animals which don't simply have the equivalent of red, green and blue receptors. They have a far more complex set of colour receptors. You can see here, again, I've shown the approximate range of our visual acuity at the top there, a spectrum running from red to violet from 700 to 400 nanometers. But this particular animal, you notice, has a dozen or so photoreceptors going from all the way peaking into the infrared here beyond 700 nanometers, going through the entire visible spectrum, and also a few photoreceptors that appear to be dedicated to the ultraviolet. Again, this isn't a biology talk, but I just want to give you a second or two to ask yourself, which animal do you think this is? And it's not perhaps obvious why this particular animal needs to have 12 different photoreceptors, but it turns out that this is a mantis shrimp. Perhaps there's a particular advantage to finding food with that many photoreceptors. I don't quite understand why. I don't really understand how on earth it can make sense of having so much data coming in from 12 different sets of colour receptors, even though they do overlap quite considerably. But we can ask ourselves, why do we have three? Some animals have far more, some animals only have two. So why do we have three sets of colour receptors? Well, it's not surprisingly perhaps a result of evolution. If we think of where we were 60 to 70 million years ago, when dinosaurs ruled the earth, we were small furry mammals that were nocturnal. We stayed out of the dinosaurs' way. They roamed the earth during the day. We came out at night to try and avoid being either eaten or trodden on. So we were nocturnal 60, 70, 80 million years ago. And once the dinosaurs were wiped out, thanks to the asteroid, then mutation took hold. Genetic mutation over the next tens of millions of years restored our colour vision, because effectively we came out from being a nocturnal small rodent and we became one of the apes. I'm not claiming that trichromatic vision is the pinnacle of evolution. Now that we're allowed to use light from the daylight, we've restored our three-colour vision. That's clearly not the end of evolution. Who knows what the evolution of mankind will look like in years to come. But again, I think you're probably all aware of the fact that we have developed sensitivity to the visible part of the spectrum, partly because that's where most of the sun is emitting its light, but essentially because that's where most of the light that reaches the surface of the Earth is centered. We can see here the transparency of the atmosphere. We see that in the visible part of the spectrum, the atmosphere is effectively transparent. It's not actually 100% transparent. There's a few percent of light that gets absorbed by a few kilometers of atmosphere. And there are other windows in the radio. So you can see why we've developed astronomy, naked eye, binoculars, telescopes, etc. You can see why we have developed that particular technology to see in that part of the spectrum. If we want to see elsewhere in the infrared or the ultraviolet part of the spectrum, we have to get above the Earth's atmosphere, which would otherwise absorb too much of that light. Of course, that doesn't stop us putting optical telescopes above the atmosphere as well, but that's not a question of absorption of light. It's simply a question that the atmosphere is turbulent, and so putting the Hubble Space Telescope above the atmosphere allows us to get sharper images. It doesn't necessarily allow us to see fainter objects. So let's return to the human eye. Remember a while ago I said we have a number of photoreceptors. I'm not going to be talking about rods anymore. We're just going to be talking about the RGB cones, the colour receptors. The image I showed before is a simplistic way of representing the photoreceptors on the back of the eye. In reality, it's far more complicated, and the photoreceptors themselves are only one layer of the cells on the back of the eye. In addition to the photoreceptors that are responsible for converting the light into an electrical signal, electrical or chemical signal, we also have a whole load of other cells, neurons. Now, perhaps you're thinking that neurons are those cells that we have in our brains, the ones that do all of the calculations, all of the perception is based in the brain. Well, strictly not true. We have a whole load of neurons in our eyes, and they are responsible for doing a lot of processing. They do processing of the images, or at least the signals that are coming from the photoreceptors. Even before those signals are sent to the brain, those are being processed by the neurons. In other words, photoreceptors are not simply catchers of light which get sent to the brain and let the brain sort it out. No, the eye does a fair bit of processing to take the strain off the brain. A lot of processing is done even before you realize that that processing has been done. And I can indicate that by this little sort of cartoon of, if we think about what's going on in a camera is sensitive to the red, green, blue light. What happens to those red, green, blue signals that are hitting each of these pixels? Well, we know exactly which filter is on which pixel. That's part of the process that made the chip in the first place. And what happens to the signals for each of the red pixels, green pixels, blue pixels? Well, they're processed into an image, and apart from the fact that some processing is done, maybe the red is made a little brighter, maybe the green is made a little darker. Yes, a white balance might be applied to the outputs. Effectively, red becomes red, green becomes green, blue becomes blue, and that is the image we get. It doesn't necessarily look quite the same as the raw image after we've tinkered with the white balance, but essentially it's a one-to-one mapping of the light we receive on the chip. That's what we see in the final image. By comparison, the eye is very different. We have red, green, blue receptors, but what happens to those signals? It is a much more complex situation before that output gets sent to the brain. Each of these nodes in this neural network, this network of neurons that sit just next to the photoreceptors, each of these nodes has a particular job to do. For instance, one of these nodes might be looking at multiple signals, not just from the red or the green or the blue. Each of these nodes might be picking up signals from the red and the green and the blue, and it might be transmitting signals to the brain which are the difference between the red and the blue, or the sum of the red and the green. It can be doing all sorts of manipulation before that information gets sent to the brain. And I can demonstrate that in this little web page, which is indicated in the bottom left, lottolab.org, if you want to go and check this for yourself. So in a room where I was doing this live, I would probably ask for a show of hands, but that doesn't work too well on Zoom. So what I'm going to do is just ask you to think for a few seconds. Here we have a cube, and I'm interested in the colours of the tiles on the top face of this cube. Now you can see a number of different colours that are present. I want you to count out of these 25 tiles that are on the top face, how many of them are blue? I'll give you a couple of seconds. With apologies for those people in the audience who are colourblind, this will not work for you, quite definitely. Having established what you think is the number for the left-hand side, now do the same, but tell me how many yellow tiles there are on the right-hand side, again, in this top face of 25, how many of them are yellow? Now, everybody should have two numbers in their head. And I'd be rather surprised if you didn't have the following two numbers. There are 4 blue tiles on the left and there are 7 yellow tiles on the right. I hope you all agree with that. You may be surprised to realise that the 4 blue tiles on the left and the 7 yellow tiles on the right are actually all the same colour. All 11 of them are exactly the same colour. And I can show you that by taking away all of the other pixels other than the 4 blue and the 7 yellow on the right that we've identified so far. I'm going to take away all the other pixels in the image, one step at a time. That is what you are actually looking at. You are actually looking at 4 greys on the left and 7 greys on the right, exactly the same shade of grey. And the only reason that you had this idea that perhaps the ones on the left were blue and the ones on the right were yellow is because the neurons in the back of your eye were processing those images and feeding information to the brain that it thought that your brain needs to know. The difference between this colour and that colour, the contrast between this tile and that tile. It was processing the image and then telling your brain what it thought was the most important information. It was not sending red, green, blue information to the brain so that the brain could work out what colour am I looking at. And that's the way colour perception works. Just as an aside, just to show you it's not just colour that the neurons are processing, it's doing the same with simply intensity levels. So if you think you can tell the difference between the brightness of one star and the brightness of another star, let me show you this. Look at the tile labelled A and look at the tile labelled B. What's the difference in brightness or intensity or grey level of those two tiles? Most people would say tile A is significantly darker than tile B. But if I bring in a sort of a mask to get rid of some of the pixels, I hope you now realise that the grey of tile A is exactly the same as the grey of the masks on the left and the right. It's exactly the same grey as tile B. This shade of grey that I'm now looping around is exactly the same. So tile A and tile B are exactly the same shade of grey. Now you know that, I'll take those blinds away, you know that those two are the same shade of grey. And yet your brain, or your eye and your brain, perhaps I should say, is refusing to give you that information. Your eye is processing that information and your brain is refusing to agree that those are actually the same shade of grey. A reminder of just how much processing is being done without you even realising it. So how do we quantify colour? If you ask a physicist to quantify colour, they'll normally respond with a spectrum. No, not that type of spectrum. Those of a certain age will remember this particular beastie. No, we're talking about the spectrum as the one the one first produced by Isaac Newton when he was trying to reproduce the album cover of Dark Side of the Moon. So back in the 1660s, it was shown that white light is composed of many colours. And at that point, we realised that there are, if you like, colours beyond the visible spectrum. In other words, ultraviolet and infrared light as well. So we know that when light passes through a prism or an optical instrument, in our case, for instance, a telescope, it reveals its wave nature. And the distance from one wave crest to the next is what we call the wavelength. And we are aware of the fact that our perception of coloured light, our perception of visible light, runs from about a wavelength of 400 to a wavelength of 700. I say about because every human is slightly different, and some people can see a little bit into the infrared or a little bit into the ultraviolet, depending on your definition. I'll stick to 400 and 700 to be the nominal visible spectrum. But that's not all there is to colour. Not all colours are spectral colours. In other words, not all colours can be found in the rainbow. For instance, if you ask yourself where is brown or where is beige in the rainbow of all colours, well, they're not there. If we want somehow to represent all colours, we can't simply put them on a spectral line. We can't simply spread them out into a rainbow and then say there's all the colours. We need some other way of representing colours. And this has been argued about for a long time, and there are a number of standard ways of doing it, but I'm going to talk about this particular standard, the CIE standard. You can see what it stands for in the top right there. It's a particular way of representing colours in a two-dimensional space, a plane which we call colour space. And as far as this talk is concerned, I am not going to worry about what the two axes actually are. That's sort of irrelevant. All we're going to say is somebody has decided that a standard way of representing colours is to plot them like this on two axes, and then all of the colours that exist end up in a two-dimensional plane, bounded with a rather odd outline, which is a result of how those two axes are defined. The spectral colours themselves fall on the outside curved edge of this rather peculiar shape. Notice that not only are they only on one edge, not the line that joins red to violet, but they are also not equally spaced. When you look at the green, you find that we have fairly large distances covering only 20 or so nanometers, and yet at the ends we have a similar distance which covers nearly 100 nanometers. Notice there are no spectral colours joining red to violet. The spectrum goes from red to violet, but that in a sense is a shortcut back from one end of the spectrum to the other. When we ask ourselves how colours are displayed, this is sometimes a little awkward because I'm looking at a particular display of red, green and blue colours all mixed together, and you're also looking at a display. It might be that you're looking at your own TV screen, it might be you're looking at a computer monitor, you might be looking at an iPad. If you're in the room, you might be looking at the display produced by a data projector, all of which will display colours slightly differently, and all of which will be capable of displaying colours slightly differently. So every device in principle is made such that you can generate a primary red, green and blue colour and mix them together to get a whole range of colours, a so-called gamut. But that gamut will not include every colour that we're looking at in this rather odd CIE space. Depending on how we define red, green and blue primary colours, mixing those colours will allow us to generate any colour inside that triangle of red, green and blue. So manufacturers of display devices try and get the red as far over to the right as possible, the blue as far down as possible, and green as far into the top left as possible to maximize the size of that triangle. But technology doesn't allow you to fill the actual color space of all colors. If you define red, green and blue primary colors, you can only generate colors that are inside the triangle. Any color outside the triangle cannot be created. So perhaps you can see, I hope, that if you move around or let your eye move around inside this triangle, you can see lots of colors from red to green to blue to cyan to magenta to yellow, etc. Perhaps you notice that if you move outside the triangle, all of these colors here look pretty much the same. And similarly, all of these colors down the bottom look pretty much the same. And the yellows over on this side look pretty much the same. In other words, this particular combination of red, green and blue, depending on what device you're looking at the screen with, perhaps you will notice that there's a very rich set of colours inside and it's very difficult to distinguish colours outside. So let's move on to think about the colours of stars. If you think of this collection here, if we ignore for the moment the limitation of a display only being able to show us a limited number of colours within that CIE colour space, let's just put that to one side for the minute and ask ourselves, where could stars possibly be plotted? If we took all the stars in the universe and plotted them in terms of their colour, where would they be? Would they be scattered over the whole of this colour space? And the answer is no. Stars cannot be any arbitrary colour. The light they emit must obey the laws of physics, specifically quantum mechanics. Quantum theory says that light can be emitted from a hot body only in a particular way. The distribution of what light is emitted at what wavelength must follow particular laws. I'm not going to talk about the details of that quantum mechanics, but it turns out that stars can only be one of these colours. Cool stars are quite red over on the right hand side. Hot stars are bluish white on the left hand side, but they must be somewhere on that line. In other words, we can't arbitrarily say, let's have a star up here somewhere. Nope, you can't have a star that shines emerald green. You can't have a star that shines magenta. Stars must be somewhere on this line, which is dictated by the laws of physics. And we can get an idea of that by taking an element here on Earth, such as an iron bar or something like that, heating up one end and allowing the heat to travel down the bar so that each part of the bar is at a slightly different temperature. On the left-hand side, the bar seems to be not glowing at all. That's because most of its energy is being emitted in the infrared part of the spectrum. But if the bar is a few hundred degrees or 500 degrees or 700 degrees, then it starts to emit a lot of red light. And as it gets hotter and hotter, that red light starts to turn more of a yellow to white light. Now, we can't necessarily reliably take that colour and convert it into a temperature, but it's a very good rule of thumb to tell us how hot an object is. Does it look red? Does it look orange? Does it look white? Gives us an idea of the colour of the temperature scale of the object we're dealing with. What's actually happening is that we're talking about so-called black body radiation. It might sound a bit odd to talk about stars being black bodies when clearly they are bright and radiating energy, but this comes from the idea that if you take a black object, in other words one that is not painted a particular colour and reflecting light from its surroundings, if an object is only emitting light because of its temperature rather than because it has a particular intrinsic colour because it's been painted that way, then we talk about the radiation emitted from a hot object as being black body radiation. And here in this diagram we see how much light is emitted, and the intensity of light is plotted by this orange line over a wavelength range from the ultraviolet through the visible into the infrared part of the spectrum. The wavelengths here run from very small wavelengths up to 3 microns. Remember, the visible range is from 400 to 700 nanometers, or if you like, 0.4 to 0.7 microns. So at a temperature given by the top right here, at a temperature, we're just starting from an example of about 1000 Kelvin or so, most of the radiation is going to be in the infrared part of the spectrum. And very little of it is going to be in the visible part of the spectrum. If we now change the temperature and say what happens to this peak that we see here, this distribution of intensities of light at different wavelengths, you can see its peak at the moment is somewhere between 2 and 3 microns. What happens if we take the temperature and raise it up a little bit? You can see what happens to the orange line. Two things happen. One is the orange line gets higher, more radiation is emitted the hotter the object. But what's even more relevant is that the peak shifts to the left. It shifts to smaller wavelengths. We're moving from the infrared towards the visible part of the spectrum. So for the purposes of this particular demonstration, I'm going to make sure that this vertical scale is adjusted to make sure this orange line doesn't simply get too high. Because if we go to much hotter objects, this orange line is going to get higher and higher and higher. So I'm going to adjust the vertical scale accordingly. What's important is the shape of this curve determined by the laws of quantum mechanics and where this peak in the curve occurs. So I'm going to take the temperature up again. We're now at 1500. We're going to go up to a couple of thousand Kelvin. Notice that the peak is still in the infrared part of the spectrum, but now we're getting some glow from the object because the red end of the spectrum is definitely producing some light. The blue end of the spectrum, not so much. Let's go up from 2000 Kelvin to 3000 Kelvin. This particular little simulation indicates that this is the temperature of a light bulb. Well, I don't know many light bulbs that get to 3000 Kelvin, maybe 2000 or so, but okay, let's stick with that light bulb. I tend to think of that as the surface of a red giant. Notice that a red giant star, the peak in its output is still just about in the infrared part of the spectrum, but now there's a lot of red light simply because this is getting so close to the visible spectrum. Red has got an awful lot of intensity here, substantially more than the blue. So red giants do emit red light, red giants do emit blue light, but they emit far more at the red end of the spectrum than the blue end of the spectrum, which is why they appear red. What if we were to take the temperature up to the temperature of the sun? We're now at about 6000 or so Kelvin. Now the maximum light output, the peak of this curve, is now inside the visible part of the spectrum. And we're now getting a lot of blue light and a lot of red light. So it might be that the peak actually peaks in the green, but because we're getting light across the entire spectrum, red and orange and yellow and green and blue and violet, we're getting light across the whole spectrum, which is why the output of the sun looks essentially white. Perhaps with a tinge of yellow, depending on how much is absorbed by the atmosphere, but essentially white light. If we take the temperature up further, the peak pushes even further to the left. So if we go all the way up to 11,000 Kelvin, now we're at our A-type star, then we find that the peak is now in the ultraviolet part of the spectrum, which means we're getting a lot more blue than we are red. Again, A-type stars emit across the whole spectrum, but much more strongly in the blue than they do in the red. So because they're emitting at all wavelengths, they are relatively white, but with a bluish tinge, simply because there is more blue than any other color in their output. So if I just go back through those stars again, the red giant peaks in the infrared and there's more red than blue. For the sun, we're effectively irradiating over all wavelengths, whereas for an A-type star, we're now mainly emitting in the ultraviolet and there's more blue than red. So the star colors, the apparent star colors, go from red to white to blue. At no point does the star appear to be a bright green. If we plot out the colours of stars in the so-called Hertzsprung-Russell diagram, which is essentially the same as a magnitude colour or a colour magnitude plot, here we have luminosity in units of the sun, and here we have surface temperature, conventionally written backwards so that the cooler stars are on the right with a surface temperature of maybe around 3000 Kelvin, the sun at about 6000, and very hot stars at 10 or 20 or 30,000 Kelvin. So remember, these colours are similar to the colours we could expect if we heat an object up in the laboratory. So there's our sun in the middle of the Hertzsprung-Russell diagram at a luminosity of 1 by definition, because the luminosity is the luminosity compared to the sun, and a surface temperature a little shy of 6000 Kelvin. We have to remember that the stars in the Hertzsprung-Russell diagram have a particular pattern. We find that the really big stars are in the top right and the small stars are in the bottom left. That's a function partly of their area determining their luminosity. If a star is very small, it has a very small surface area, so it can't produce a very high luminosity. Whereas if a star is relatively hot or even relatively cool but a huge size, then it's got a lot of square meters to radiate from, and therefore it can be very luminous. If we think about stars in the main sequence, we find that all the large mass stars are in the top left of the main sequence, which runs from the top left to the bottom right. And the bottom right of the main sequence corresponds to small mass stars. This turns out to be quite useful if we're trying to understand, for instance, the nature of a star cluster, such as this globular star cluster. If we wanted to know something about the origin of this star cluster, rather than simply saying, well, isn't it pretty, we've got a lot of stars and a lot of different colours, if we wanted to know when this star cluster was born, how old is this star cluster, one option we have is to image every star. Now, in a very dense star cluster like this, where you need a high resolution telescope like the Hubble Space Telescope in order to be able to separate and resolve stars hopefully close to the core of the cluster. But even without that resolution, we can still in principle image a star cluster and look at every star and measure its magnitude and its colour. Its magnitude is a measure of its luminosity, because we may not know how far away this star cluster is, but we know that all of the stars in this cluster are at approximately the same distance, and so a measure of the apparent magnitude is a good indication of the star's absolute luminosity. So for all of the stars in this cluster, thousands, tens of thousands, perhaps even hundreds of thousands of stars, we can measure for each star their luminosity and their colour, and we can plot them on the Hertzsprung-Russell diagram. And we find a lot of them might fall on the main sequence, indicated schematically by this collection of white dots. Yes, there will be a whole load of other stars as well. There will be some giants and supergiants in the top right, and there could well be some white dwarfs in the bottom left. But I'm interested in those stars on the main sequence. Because remember, the ones in the top left are the really massive stars. These are the ones that have very short lives. Because of the enormous forces of gravity, with very massive stars, gravity is going to be a very strong force, and therefore you need to burn your fuel very rapidly to counteract the force of gravity. So blue supergiants have very short lives in the top left. Conversely, in the bottom right end of the main sequence, red dwarfs, being very small, gravity is not that strong, and therefore the fuel, even though there's not that much of it, the fuel can last an awful long time, not just millions of years, not just billions of years, but perhaps trillions of years, lifetimes, or tens of trillions of years, because the force of gravity is so much less for small mass stars. So because we have short-lived stars in the top and long-lived stars in the bottom, we can use the indication of how many stars we see in the main sequence to tell us how old the cluster is. Because if we find that the main sequence stars go almost all the way into the top left of the Hertzsprung-Russell diagram, that tells us that the cluster must be very young, because we know those stars don't live very long in the top left. So if we see them there, then it must be a young cluster. Whereas if the main sequence stops short of that point, we can, using our understanding of the way stars behave and how mass determines the lifetime of a star, we can figure out how old that cluster must be. So if the main sequence only goes to that point, we can determine that the cluster must be about 1 billion years old. If the main sequence stops as soon as we get to a region around about where the Sun is, indicated by the arrow, we know the Sun has a lifetime of about 10 billion years, and therefore if the main sequence that we see stops at that point, that tells us any stars that are more massive than the Sun have already ended their lives. Those stars would only live for less than 10 billion years, and so we can determine that the cluster is about 10 billion years old. So using the colours of stars, it's very useful to tell us something about the history of star clusters. Stellar classifications can sometimes be useful. Rather than simply talking about the surface temperature, it's sometimes useful to actually assign a letter. I've already used that when talking about colours. For instance, an A-type star I mentioned earlier. M and K corresponds to the rather dull red giants and red dwarfs. G is something close to our Sun, and A, B and O are the very hot blue stars. If we look at their spectra, we can remind ourselves that although they have different surface temperatures and hence different spectra, all of the stars emit across all wavelengths. It's simply a question that for the very hot stars, they emit much more intensely in the blue and violet part of the spectrum and rather less intensely in the red. And similarly, the cool stars, such as red dwarfs or red giants, again emit at all wavelengths, but they emit far more in the red than they do in the blue. Remember those black body curves that showed us how the peak shifts as a function of temperature. You could ask yourselves, well, if some stars look red and some stars look blue, what if we were to add up all the light of all the stars in all the galaxies? What is the average colour of the universe if you assume that the colour is determined pretty much by all of these luminous stars? That's not necessarily the case, but it's a good approximation. What is the average colour of all the stars in the universe? Well, this was done by some astronomers that obviously had too much time on their hands. They looked at surveys of lots of galaxies and looked at the spectra and determined, if you add them all together, what's the overall colour of the universe. And they came to the conclusion, by adding up 200,000 galaxies within a couple of billion light years, that hopefully is fairly representative, they found that. A rather boring beige. And rather than call it beige, they tried to make it more exciting by calling it cosmic latte. Or my favourite, skyvery. What a wonderful name for the colour of the universe. So we've been thinking about colours of stars. Let's think about colours of nebulae. Stars and galaxies, again, let's assume that galaxies are simply collections of stars. That's a little oversimplification because of galaxies have got gas and dust and other things inside them. But let's assume that galaxies are just collections of stars. And we've already thought about stars, and essentially we get a continuous spectrum. Yes, it won't necessarily look like that. It might be that some stars are a lot brighter in the red, some stars are a lot brighter in the blue, but essentially all stars emit light at all colours. But if we look at nebulae, the rather rarefied gases that exist in galaxies, we find that nebulae emit, generally speaking, at very specific energies. So for instance, there might be 1 or 2 or 3 lines in the visible part of the spectrum. If we were to extend that to the ultraviolet and the infrared, we would find a whole load of specific colours being emitted by these nebulae. And we can ask ourselves why that is. If we imagine what an atom looks like, this is a rather, again, cartoony version of an atom, but it's not right for a number of different reasons, and this is how we tend to think about atoms: a positively charged nucleus surrounded by a whole load of negatively charged electrons. But the main problem with a sort of image like that is it doesn't remind us that all of the electrons actually have different energies. In this particular cartoon, all of the electrons look the same. They all apparently are doing the same thing and presumably have the same energy. So it would be somewhat better to think of the electrons buzzing around the nucleus as being more like that. Not exactly a solar system, but at least it reminds us that all the electrons are different, or at least occur in families which are different. Now, unlike a solar system, the electrons in an atom are not confined to a plane, which is why we should really think of them as being three-dimensional concentric shells, as indicated by the bottom half of this diagram, where the shells have been cut in half. But for the purposes of just getting an idea of how the electron energies behave, the top picture will do well enough for the time being. Quantum theory tells us that an electron in an atom, we're not indicating where the nucleus is here, and we're not dealing with very complex atoms. Let's just think about one electron in an atom, and it can exist in a number of different energy levels. Something akin to orbits around the sun for planets, but not quite the same. This is a quantum system, not a clockwork system like the solar system. If an electron jumps from a high energy level to a low energy level, where does the energy difference go? If the energy is lost by an electron, that energy can be emitted as a photon, and the photon of light carries away the energy that's lost by the electron dropping from the high energy level to the low energy level. And similarly, it is possible for light, if it has exactly the right energy, an incoming photon of light, if it has exactly the energy difference of the low energy and the high energy, a photon of light can come into the atom and be absorbed, and the electron jumps from the low energy to the high energy. So summarizing both of those, an electron can jump between different energy levels, and if it loses energy, a photon can be released. And if a photon is absorbed, it can jump from one energy level to another. But bear in mind what's said in the bottom left there. A photon can only be absorbed if the energies are an exact match. You can't simply take any old photon and expect the electron to jump anywhere. It can only jump to one of the defined energy levels which exist for an atom. Those defined energy levels are determined by the laws of quantum mechanics. So a photon of light with a given energy, it turns out, has a particular energy and a particular wavelength and a particular color. In other words, we've been talking about different colors of light having wavelengths from 400 nanometers in the violet part of the spectrum up to 700 nanometers in the red part of the spectrum. We could equally well talk about low energy photons and high energy photons. There's a one-to-one translation, if you like, between a particular energy and a particular wavelength and a particular color. And hence, if we're talking about quantum mechanics telling us that atoms have specific energies, that means particular energy differences will have specific colors. So every atom, generally speaking, has lots and lots of different energy levels. It's just not the two that I showed in the previous diagram. There are, in principle, an infinite number of energy levels, and electrons can jump between lots of different energy levels according to rules which again are determined by quantum theory. But if there are specific energies that are characteristic of a particular atom, hydrogen does not have the same energy levels as helium. Helium does not have the same energy levels as carbon. Every element in the periodic table has its own characteristic set of energy levels, and hence it has its own characteristic set of colours that will be emitted or absorbed depending on whether an electron is losing energy or gaining energy as it transitions between these levels in an atom. So in a sense, the specific spectrum is a fingerprint of the atom we're dealing with. And if we're looking at light from a nebula, a rather diaphanous gas spread throughout the galaxy of interest, then those colours will depend on the atoms in the nebula. If the nebula is made of hydrogen, there'll be a particular set of colours from hydrogen. If the nebula is made of oxygen, there'll be a particular set of colours from oxygen. But we've already seen that with light from a star, the intensities effectively cover the entire visible spectrum, with an intensity range that can vary from one star to another. And the colour intensity range across the spectrum will depend on its surface temperature. But it's not the discrete set of colours that we see from a nebula. But stars and nebula are, generally speaking, made of the same stuff. They're both made of atoms, and stars and nebula are both made of hydrogen and helium and oxygen and carbon and all these other atoms in various combinations. So if they're made of the same things, why is there a difference between the spectrum of a star and the spectrum of a nebula? Well, the difference boils down to the density of the object that is emitting the light. If the atoms are well separated, meaning if the atoms are separated by distances which are large compared to the notional size of an atom, then each atom will emit colours as dictated by the laws of quantum theory. Whereas if the atoms are close together, always bumping into each other, then they can share energy with each other, and the discrete colours that you would expect from an individual atom get smeared out into a continuous spectrum. So the bottom line is, if we want to tell the difference between a discrete spectrum of particular colours and a continuous spectrum of colours, we have to think about, well, how close together are the atoms? Let's just ask ourselves, how many atoms are there in 1 cubic centimetre of various bits of stuff? Let's start with something here on Earth. How many atoms are there in 1 cubic centimetre of a typical lump of metal? A lump of aluminium, 1 cubic centimetre, the size of a sugar lump. How many atoms does it contain? It's about that number. Some huge number of, 100,000 million. A big number. How many atoms are there in 1 cubic centimetre of the Earth's atmosphere? Earth's atmosphere is a gas, so substantially less, but clearly still an absolutely huge number. The atoms in the Earth's atmosphere are continually bumping into each other. What about the sun's surface, the photosphere? Perhaps surprising that there's rather less of those atoms than there are atoms in the Earth's atmosphere, but still an awful lot of them. Still, we've got, 100,000 million, substantially less than the amount in the Earth's atmosphere and the amount in a metal, but still a huge number. So the atoms in the sun's surface, again, are continually bumping into each other. What about the sun's corona, the sun's atmosphere? Notice the reduction in the number of zeros. The sun's corona is very, very, very tenuous compared to the sun's surface. So yes, the sun's atmosphere might be very hot, the corona might be millions of Kelvin, but there are very few atoms or particles to carry that energy around. Let's go one step further. Let's ask, how many atoms are there in 1 cubic centimetre of, let's just take a typical nebula in the Milky Way. Less by orders of magnitude, a mere 10,000. These atoms are hardly going to know about the other atoms in this cubic centimetre. What about the interstellar medium? Only about 1 atom floating around in every cubic centimetre between the stars. And finally, in the intergalactic medium, I put 0. It's not technically 0, it's just that you're not likely to find one in 1 cubic centimetre. It might be 1 per cubic metre rather than 1 per cubic centimetre. So there is stuff out there. And when you think of the distance between galaxies, you might think it's irrelevant how much stuff there is out there, but actually there's a huge number of atoms between galaxies simply because there is so much space between galaxies, even though the density is quite low. And indeed, people spend their time looking at the intergalactic medium because it's a medium that should not be ignored. There's an awful lot of atoms out there. But in terms of density, we can see that the first three are very large numbers, and that's why light emitted by a lump of metal when you heat it up, or the Earth's atmosphere, if it ever got warm enough, or the surface of the sun, are effectively continuous spectra, because the atoms are bumping into each other so often. But as soon as we get to something like the sun's corona or a nebula, there are so few atoms in a given volume that the atoms hardly ever bump into each other, which means they behave as if they are totally isolated from all of their neighbours, and the light they emit is essentially the light you would expect to get from isolated atoms that give you a spectrum, a discrete set of colours dictated by the laws of quantum mechanics. So that's why there's a difference between how stars appear and how nebula appear as far as their colours are concerned. Let's just have a think about spectroscopy. Taking light from a distant object and separating it into its constituent colours can be useful for a number of different reasons. For instance, we know from the so-called Doppler shift, the fact that if an object is moving relative to our line of sight, then the apparent position of absorption lines, in principle emission lines, but if we're looking at the emission from a star with absorption lines, we can see those absorption lines shift, because when an object is coming towards us, those lines get blue shifted, and when the object is moving away from us, those lines get red shifted. In this particular case, we're assuming we're looking at the light from this star, which has a planet going around it. So we might not be able to see that planet, but we can still see the Doppler shift of light from the star as it's sometimes moving towards us and sometimes moving away from us, as both the star and the planet rotate around their common centre of gravity. So if we look at the light from a star and watch what happens over a period of time, if we see the absorption lines moving backwards and forwards and backwards and forwards, we can deduce that the star is moving away from us or towards us, and hence we can deduce the existence of either a companion star which we can't see, or perhaps an exoplanet which is too faint to be seen. So breaking light down into its constituent colours is not only useful for telling what is the object made of, because we can tell from the spectrum what the constituent atoms are. If we look at features such as the Doppler shift, we can tell how things are moving, and we can determine the existence, or at least infer the existence, of objects we cannot see. Another useful way of breaking the light down results from, because we live in an expanding universe, and an expanding universe is effectively stretching the light as it travels through space. If we think about visible light being emitted from a distant galaxy, as it travels through space which is getting stretched, the wavelength gets increased or redshifted, because red is the longer wavelength end of the visible spectrum, and so it's possible that ultraviolet or visible light gets redshifted either towards the red end of the visible spectrum, or perhaps even into the infrared part of the spectrum as the light travels through space. So the idea of measuring the redshift, because the universe is expanding rather than contracting, apart from very local galaxies, all of the more distant galaxies are all moving away from us because of the expansion of the universe, and we can measure that redshift, and we can determine how far an object is from us by measuring the redshift, which is given the symbol Z. If we work out how much it's been shifted compared to its original wavelength, that is given the label Z for redshift, and objects at large redshifts correspond to more distant parts of the universe. So the redshift on a cosmological scale is an essential way of determining the size of the universe. If we think about a redshift of 1, in other words, the wavelength has doubled since the light left the original object. By the time it arrives at Earth, the wavelength is twice what it originally was. That's a redshift of 1, because the stretch is 1 times the original wavelength. To give you an idea, that corresponds to an object that is approximately 10 billion light years distant. So we're not talking about galaxies which are only millions of light years distant. We're talking about cosmological scales here. And a while back in 2020, during the COVID lockdown, I tried to image an object which has a redshift of z equals 4.3. In other words, its wavelength once it's arrived at Earth is some 5 times larger than when the wavelength, the light originally left this particular object. It's a quasar, which means a galaxy with a very bright nucleus which is visible at some incredible distances. This particular object was some 25 billion light years distant, and at that sort of distance, it means this object, this quasar, is actually receding from us at about twice the speed of light. It's quite incredible that even though it's receding at twice the speed of light, it's still possible to catch the photons emitted by a galaxy like this. When I originally processed the image back in 2020, I found that is the quasar. Not a very spectacular image, I will give you that, but the fact that the photons that produce that little dot in the middle have been travelling for over 12 billion years. Remember, the lifetime of the universe is only 13.8. These photons have been travelling for 12.4 billion years before arriving. I thought that was spectacular enough, but I thought for this talk, would it be worth processing this and retaining the original colour? And that's what I've got on the right. It's a little more difficult to see because it is a very dull red colour. Perhaps not surprising because it's at such an extreme distance, because it's receding from us at twice the speed of light. The colour is very much redshifted, and so regardless of what the original wavelengths were, probably in the ultraviolet part of the spectrum, they've been redshifted, and now we're just getting a hint of a little bit of red left. Most of the light will probably be in the infrared part of the spectrum. But if I take that image and ask, what does it look like if I separate the red, green, blue? Remember, when you take a colour image, this was taken on a Nikon DSLR, if you take a colour image, then you automatically get red, green and blue, which you can separate out if you so wish. So this particular object is clearly present in the red part of the red channel of this image. I'm not sure if you can see it, but it's only just visible that there is a tiny bit of green in this image, and there's essentially nothing there in the blue channel of this red, green, blue image, which is one of the reasons I originally processed it as a monochrome image, because I didn't think it was worth preserving the light. But I'm telling you this simply because that's the way other telescopes work. If we look at, for instance, some of the more recent James Webb output, they've been doing exactly the same thing. In principle, they would like to take the spectrum of each of these objects to work out how far these galaxies are. Some of them might be very remote, some of them might be rather closer. But it takes time to take a spectrum of all of these galaxies, especially when you've got thousands of galaxies in your field of view. So the quickest way of getting a rough and ready idea of how far away these galaxies are is to do what I've just shown you. Work out how bright the object looks at this wavelength, how bright it looks at this wavelength, and this one and this one. I effectively did it at 3 wavelengths, red, green and blue. The James Webb Space Telescope does it at half a dozen different wavelengths. And it finds that it's quite, this object here, doesn't really matter which one it is, this object appears to be quite bright at a very long wavelength, and then it looks rather dimmer if we go to shorter wavelengths. So all of these wavelengths are infrared, so don't be fooled by the colour running along the top. That's just indicating short wavelengths to long wavelengths. And based on the idea that this object looks quite bright in the longer wavelengths and quite dim in the shorter wavelengths, they put a provisional indication of what its redshift might be. And this caused a lot of kerfuffle in early James Webb output because they thought they were perhaps looking at very large redshifts. It turns out, no, they aren't. This way of determining the distance to an object and the redshift of an object is only approximate. We're just using the colour to give us an idea of how red this object is and to give us an idea of what its redshift might be. But actually, when they went back to these objects and did the full analysis with a full spectrum, they found that these objects were not quite as distant as they thought, and they had to revise the distances to a number of different galaxies. So that's just a sort of cautionary tale. When you see some of the very early James Webb Space Telescope output, there were a lot of sensational headlines, some of which were the result of the fact that the data was only preliminary because they were showing you what objects look like at different wavelengths, rather than taking a spectrum and actually measuring the redshift in order to get the distance to these objects. We can imagine what happens if we go beyond colour, because the question we always get as astronomers is, whenever I look at a Hubble Space Telescope image, does it represent the true colours? Does it represent what I would actually see if I was sitting there myself? We've all seen these pictures like the one on the right of the pillars of creation. And people ask, especially those who haven't got any experience with how photographs are made, will often ask, is this genuine colour? But we have to remind ourselves that Hubble is not in the business of making pretty pictures. That's a side issue. It's trying to work out what is actually going on. It's trying to make scientific discoveries of what these objects are and how they're behaving. And for this sort of object, these sorts of nebula, it turns out that throughout the visible spectrum, the elements that seem to keep cropping up in these nebula are hydrogen, no surprise, the most abundant element in the universe, but also a fair amount of oxygen, and perhaps a little surprisingly, sulfur is quite common as well. And these three arrows show you the wavelengths at which sulfur and hydrogen and oxygen emit most strongly. And therefore, if you have filters that let through light at the hydrogen wavelength, light at the sulfur wavelength, light at the oxygen wavelength, you can combine those to make a very scientifically useful image. But what colours are you going to assign to these three bands, these three wavelengths? Because notice that sulfur and hydrogen, although they are distinct elements, just by accident, they happen to emit at very similar colours, very similar wavelengths. So separating them and taking images with different wavelengths allow you to see what the hydrogen is doing and what the sulfur is doing. But you wouldn't make a colour image in which both of these are red, because they would look pretty much the same. By eye, you would not be able to separate them. So what they actually do is they take sulfur and they basically take the sulfur image and they make that one red. They take the hydrogen image, they make that one green. They take the oxygen image and they make that one blue. So they're not real colours, because hydrogen emits in the red, but in a Hubble, so-called Hubble palette, it's actually coloured green. But they do that simply because sulfur is sitting there and that's hogging the red slot. They try and keep things in the same order. So you notice that in terms of actual wavelength, we've got sulfur, which is the longest wavelength, then hydrogen, then oxygen. And we're mapping those to red, green and blue, the longest wavelength, the middle wavelength, the shortest wavelength. So we try and keep them in order. And that's the sort of rule of thumb. If we're going to be using non-real colours, non-true colours, at the very least keep them in the same order, even though they're not their true colours. So if we do that with the Hubble Space Telescope, we end up with red, green and blue indicated there. When you add those three together, you get the colour picture that we all know and love on the right-hand side. If we represented them in their true colours, it would simply be glowing red, because there's so much hydrogen in these nebulae. If, as an amateur photographer, you've ever tried taking a picture of the Eagle Nebula, you will find that it basically just glows red because of the hydrogen content. By separating the colours like this and making a false colour image, you can see more detail of what's going on. And that's true for most, not necessarily all, Hubble images. The Hubble palette is a very popular one to use for Hubble images, and a lot of amateurs use the same Hubble palette if they're doing the same thing, taking images of nebulae using these three specific wavelengths. When Hubble is taking pictures of galaxies, because galaxies are emitting across the entire visible spectrum, they tend to be in true colour rather than the false colour of the Hubble palette. And of course, the visible spectrum we know is only one small part of the whole electromagnetic spectrum, and we're not going to talk much about the rest of the spectrum, but the obvious one is in the infrared. The James Webb Space Telescope works there, so you can genuinely say none of its images are true colour, because all of its images are taken in the infrared part of the spectrum. So they have to do exactly the same as the Hubble. They take images with particular filters that correspond to particular wavelengths. Which filters they use will depend on what object it is they're trying to image. And then, having obtained 3 or possibly more images, they will then assign them particular colours whilst keeping them in the same order, and then produce colour images. And of course, because those colour images are chosen for red, green and blue so that we can appreciate them, they are simply shifted relative to the original wavelengths, which are all, as you can see here, perhaps you can't read the writing, these are all 1 micron, 2 micron, 3 micron, 4 micron, all well away from the visible part of the spectrum. And this is one of the James Webb Space Telescope filter wheels, and it has more than one of these filter wheels, lots of different filters to allow them to have wideband or narrowband filters depending on what it is they're trying to image. And one example of that is this image taken a while ago of the Tarantula Nebula, one of the largest star-forming regions that's in the Magellanic Cloud. Here we're zooming into part of the Tarantula Nebula and then zooming in again to see what's going on around a star. And here you can see the red, green, blue channels of this particular colour image are chosen at specific wavelengths of 3.3, 2.1, 1.8 microns. These aren't arbitrary. These have been chosen because the wavelengths have been chosen to show the detail of what's going on in hydrogen, atomic hydrogen or molecular hydrogen. So these wavelengths are known to be characteristic of what's happening if hydrogen atoms are separate, or what's happening if hydrogen atoms have got together to make hydrogen molecules. This is quite important because whether it's molecular hydrogen or whether it's atomic hydrogen will affect the way stars are born, because they basically they get rid of heat from the collapse of a hydrogen cloud in different ways. And you can see that where the hydrogen is not the same as where the molecular hydrogen is. The third wavelength here is showing you what hydrocarbon dust is doing, because again, it is thought to be rather important as to what's going on in the dusty region around a star when stars are being born. So here the different wavelengths are chosen for scientific reasons, and they have chosen to colour them as red, green and blue, while preserving the fact that the longest wavelengths in the infrared are mapped to the red and the shortest wavelengths in the infrared are mapped to the blue, so the ordering is maintained. That's the general rule of thumb. They're not natural colours, but they are as close as possible within the confines of taking invisible infrared and converting it to visible images. So let me summarise. The takeaway messages are really that the eye is not a camera. It does not simply record the intensity of red, green, blue light and feed those red, green, blue signals to the brain, which is then responsible for generating a red, green, blue colour image. The eye does a lot of processing to minimise the amount of information that has to be sent down the optic nerve from the eye to the brain. There are lots of neurons doing a lot of work. The colours of stars are determined by blackbody radiation, and they range not from red to green to blue, they range from red to white to blue. There are no emerald green stars. If you think you're looking at a star which has a tint of green in it, it's probably the result of what I showed you earlier, the fact that you can be fooled and your colour perception is affected by neighbouring stars or neighbouring objects. The colours of nebulae are determined by quantum jumps in their constituent atoms. Because the atoms in a nebula are so far apart from each other, they're not aware of each other's existence, and so the colours from the atoms in a nebula are the colours that you would expect from isolated atoms. And finally, breaking down light into a spectrum can be useful not only to allow us to see the actual atomic composition of, for instance, a nebula, so that we know it's made of hydrogen and sulfur and oxygen and perhaps other elements as well, but by looking at how features in a spectrum change, we can determine how things are moving. So we can determine the existence of multiple stars or the existence of exoplanets around stars. And by tying in the redshift to the expansion of the universe, we can determine the distance, or at least we can calculate the distance to very remote objects by looking at the spectrum of those objects. So colours can indeed tell us an awful lot about how the cosmos works. Thank you very much for listening.